sorry for interrupting.
And we were at a break ourselves.
Have a nice day.
Yep, you too, Dominic.
That's what we were thinking, that's why you.
What are you?
Just, okay, no, you're saying earlier. For sure. Nothing happened.
I don't think it. That's what they.
You can come to your show and take care of the kids. Right.
I'll see.
No, no, but.
So I guess I'm still recording. Yep.
I have the picture cards that, you know, and I won't
All right, so let's pick this up. Figure out how much it's gonna compress. We got the skier. So we got the skier. Let's make them something generic. Average mass.
How do we know it's, we're trying to find the potential energy because it's a spring that we're trying to compress? How far would that be? Spring?
Yeah, so it's all about, he starts out with all this potential, it becomes kinetic, it changes back into something.
Okay.
It's, because there are conservative forces involved here, it's only gonna change from one form to another. So kinetic can only change into potential of some type.
Okay.
Is that sufficient?
Yeah, I just wanna make sure I know how to, which equation to use.
The only three forces acting on it.
Okay.
There's weight, conservative force. There's gonna be the ideal elastic, conservative force. And normal force, which doesn't do any work. So, I know my total energy initially equals the same final. I got kinetic plus two different types of potential. I'm gonna do S for spring. So we got kinetic energy and two types of potential energy, because I have two conservative forces involved. So, initial. K final plus UG final plus US final. You ready? Here we go. What's the formula for kinetic energy?
1/2
M squared.
Okay, still not as great as the first one was, so you set the bar really high the first time. MV initial squared. What is the formula for potential energy associated with weight? All right, I'm not gonna bother writing the C because it's gonna cancel out. What is the potential energy formula associated with an ideal spring or elastic material?
1/2
You started fading right there. I heard 1/2 times K. Yeah. 1/2 K, little k, is not the same as that K, it's small k, times delta X squared is equal to initial, is equal to the same stuff final. So I need to explain what those are still. MV final squared plus MGH final plus 1/2 K delta X final squared. All right, dramatic pause for questions, especially about handwriting.
So it's the same thing in the first one, but just with final.
Yes, absolutely.
Where do we get the spring from?
This bit right here, from the spring. Now, I did it up on the board over here, I didn't explain it, I just said that if you're dealing with an ideal elastic, that the force was negative K delta X, and the formula is 1/2 K delta X squared. All right, so what do these things mean? K. K is known as the spring constant. So for 1/2, so use of S, 1/2 K delta X squared. This is the spring constant. And it's basically a stiffness constant. It's how much force do I need in order to stretch this thing a meter? So if it were 2 newtons per meter, that means that for this spring, it would take 2 newtons of force in order to stretch it a meter or compress it a meter. To go 2 meters requires 4 newtons. 10 meters, 20 newtons. Just that times however much you're going to stretch it or compress it. Delta X is how much it has been stretched or compressed from its just natural state. If I have a spring, it's just kind of hanging there. So there's the slinky. So I have a slinky. It has a natural just hanging length. And delta X would be, if I attached a mass to it, it would stretch down a little bit more. How much it stretched from where it just naturally hangs with nothing on it. Preferably non-sticky marker. So that's the spring constant, or I'll put in parentheses stiffness. The larger the number, the stiffer the spring. And delta X is
Stretchiness.
your compression. And so basically how far from natural length.
I'm here for a test.
Nice dramatic entrance. We're gonna take a small little break here. Just enough for me to hand him something.
That's right. I know it's not
He's just that. I looked at
Yeah.
What are you doing in the prayer person?
I'm trying to remember something. It's all around. They're writing something. I think it's a long time ago. I can't remember what class it is.
I just have a password everybody knows.
I really cannot like it.
That's the problem.
Yeah. I have all my texts.
On Sunday?
Yeah.
I know, it says they get there before 4. At 4 o'clock. 12.
I think they're,
So I think about this.
412?
Yeah.
Oh, I have the church.
what is it?
Oh, we're gonna go like 3:30. Yeah.
We can like a wall that we're around
Yeah.
like.
We can go early.
But
or
don't
late.
see us
That's what it
right.
must be.
Then.
Yeah, so we can
if
do
you're
it.
missing out.
I can't be this man.
No.
Isn't he?
I just wanna get to that way.
Go back to
Everyone
watching
is
it.
happy.
No, they will.
Back together.
Because I'm gonna go.
And then it's gonna be all good.
No, everybody screams though, everyone says fun.
Well, I'm gonna scream at when I.
I think it's really fun.
I think so too. I'm just scared.
So just end it.
I know I'm scared.
If you think.
I remember when I was a little
Don't
kid,
trust yourself.
I did she's
go
the
back
horse
to
and the
that
horse
one.
like ready. And the horse chased
That's a
me.
little hard.
I think I have like PTSD from horse. Because
That's
Yeah,
not fair, that's hard.
If you
That's
don't-
not hard, but it's not.
It's better for you,
horse is
Yeah.
dangerous.
so you can move on.
You can't outrun a horse.
Cause now you're gonna think.
Yes. And then the pigs used to chase me, the ghosts used to chase me.
Yeah.
I think they can sense like that you're scared.
You know, kids eat.
And then there's gonna be a loop.
Okay, okay, I'll do it when I get home. I don't wanna do it now.
No.
Yeah, don't do it now.
There used to be a
Think
park.
about it.
Yeah, I was like, I'll do it.
And they have
I
big
just got
hall,
it.
and then whenever they got time,
Refunded the
that and that, and they kept.
Okay.
Is that what it was?
Yeah, but it was like their pet hall, so
How do you eat your pet?
It's not.
we pet the covering.
I mean, you're good at a chance.
I went back in my head. Yes,
If you cared, you would.
I would never eat it.
True.
I had rabbits.
Would you eat them?
No.
Alright.
What happened to chicken?
What? Oh,
I see it now. I can see that he's
I've seen it too. And it's up its tongue. That's nasty.
It's temporary.
I
I think it'll be temporary.
All right, thank you for your patience.
See, that's what's happened to me.
All right, so back over here. So what can we get rid of? What's equal to 0?
The initial height.
Okay, if you want to. So you want to make the initial height 0. Because Brian says so. So he's establishing height is equal to 0. All right. What else? Well, you go part by part. I know 1/2 is at 0. His mass is at 0. Is his initial speed 0? Excuse me.
Yes.
Okay. So the initial speed is 0. K's, oh, I have to give you a K. We'll make K equal to 40 newtons per meter. So, K's not 0, half's not 0. Is the initial stretch or compression of the spring 0 or not 0? The spring's just sitting there.
0, right? For the initial stretch, 0.
Yeah, 0. Something said it, so 0 because it's just an initial condition. Delta x initially is 0. Final speed?
Zero.
Yeah, because if he's still moving, the spring is still getting more compressed, so we're looking for that maximum compression. So that's that point when he stops. So that's 0. Because his final speed is 0.
So his final
Final height?
I'm sorry, so his final speed would be him pushing as much as he can to get the compression to be half of the spring?
Yeah.
Okay. So
And
he's like
that's the
standing
turnaround
there.
point.
Okay.
Final height?
We said that was 0.
That is
meters.
correct.
So
Therefore, is the
negative-
final height 0?
Negative 50.
Negative 50.
It'll be negative 50, all right? And final displacement definitely is not zero, because that's what we're trying to find. So we were taking this seemingly complex formula and reduced it down to just two things. We have because of Bryant, we have no energy to start with. And we end with mgh final plus 1/2 little k delta x final squared. Everything else went away. Trying to solve for delta x, we can plug in numbers at this point. His mass is 70 kilograms. G, 9.8 meters per second squared. H, we established is negative 50 meters, plus 1/2 times K, which is 40 newtons per meter, times delta X final squared. The math problems, let's ignore units for the moment. Zero equals 70 times 9.8 times negative 50 plus 1/2 times 40. That's the math problem. I would say let's multiply what we can. What is that? The other one I won't do. That's plus 20.
Negative 3, 4, 3, 0, 0.
Negative 3, 4, 3,
0,
0,
0. 2
0,
zeros.
0. Okay.
Yep.
I'm trying to get x all by itself, so why don't I take this over to the other side. So I got 3, 4, 300 equals 20x squared. Now what?
Divided by 20.
Yep, trying to get x all by itself, so I have to start getting rid of all this extra stuff. So x squared equals 1715.
Sorry,